Hello class, this is Ms. Ayodeji with today's video on 9.1 sequences. As you're watching the video, please remember to use your notes and write down important vocabulary, formulas, equations, or examples. Feel free to pause, rewind, or replay the video as often as you need so you can get a clearer understanding. And at the conclusion of watching the video, write a brief summary of what occurred in your notes and submit that summary as well as a top question via the online WISC form. Don't forget to work on the practice problems and go through the examples in the section so that you can have a better understanding as well. Let's begin. If you recall from pre-calculus, a sequence is an infinite list of numbers, but it usually does have a starting number, and that number can be any number. And in this case, we reference it as the leading term or the first term, and we indicate it by S sub 1. If the name of the sequence is S, sub 1 represents the order of the sequence and it's the first, and S sub 2 and vice versa. We indicate, therefore, that the sequence operates kind of like a function because it does have a domain, and the domain values are the whole positive number starting from 1. Some books start from 0. And you can, but in this book, we're starting from 1, and they go on infinitely past that. Now, the range will vary based off the sequence, and sometimes we can describe a sequence by a general term, S sub n. But not all sequences can be described by a formula. But the sequences we'll be looking at, most of them can be described by a formula in more than one way. Here's an example of a sequence. And this is a general term of the sequence. And ideally, initially, the first term is always S sub 1. So we replace 1 in the formula and we get out our answer. We replace 2 in the formula, get out our answer, vice versa. So the first 6 terms of this sequence look something like this. Now, of course, the sequence can go on forever depending on how many n values you place in, but these are the first 6 terms of the sequence. And we like to represent the sequence in terms of a fraction if the general term is in terms of a fraction. Plus, it can be more useful to us. But sometimes you'll be asked not to determine the terms of a sequence, but actually determine the general term of a sequence. So here we have a sequence of numbers. As you can see, the dot, dot, dot indicates it's infinite, and the first term looks something like this. And we're going to try and come up with an expression to represent S sub n. Now, the thing that I want to point out when we're talking about S sub n is S sub n is depending on the nth term. Oops, cannot write that right now. So I know from a pattern, this looks to be the numerator is going to be 7. And if I change this to a fraction with the numerator being 7, then this is really 7 over 14. So my numerator looks like 7, and then if I see what's going on with the denominator, I see that the denominator values tend to be increasing by 3 each time. So it looks like it's going to be 3n is the rate of change, and then since the starting value is 2, I need to come up with an expression where I'll get the denominator being 2, and so I subtract 1. And as you can see, if we test it for the 8th term, S sub 8, oops, sorry, my handwriting is real. I know it's going to look like 7 divided by 3 times 8 minus 1, which is 23. And that indicates the 8th term. And if we were to do the same process and add 3, we would get that answer, 7 over 23. 1, 2, 3, 4, 5, 6, 7, 8. All right, so it works. That's our rule, our general term, okay? You can also represent sequences graphically, as we can see here. Depending on the sequence values, it depends on what kind of graph you use, whether a Cartesian coordinate plane or just a number line. Depending on here, the n axis represents the indices, and the S sub n axis represents the values. And here, this axis just represents S sub n, and we label each coordinate point in this case. All right, moving on. Another way to come up or determine sequences or the general term is not just a general term that's based off n, but a general term that's based off previous term values, and that's called a recursive sequence. So let's take a look, and here's an example of a recursive sequence where I start off with the two values of s of 1 as 0 and s of 2 is 1, and then I define the next value by the two previous values. Okay, and this looks like this. Another example is this term at n times s of n minus 1, and it looks like this. So the first term is 1 times 2 times 1, and that's 2, and 3 times the previous term, which is 2, is 6. And most of you can able to identify this looks very much like a factorial. If we're on the 1, 2, 3, third term, this is going to be 3 times 2 times 1. If we're in the fourth term, so this is recursive, and so is this one, but this one is not recursive. So these are all general terms, they're just not recursive. So let's find a way to determine a recursive definition of sequences. And in this case, as you can see, we're just focused on this one right now. If I take a look at the differences, it looks like the differences, this is increased by 2, by 4, by 8, by 16. So it seems like there is some type of pattern there, but I'm trying to define this recursively, and the best way to define it recursively is let's start with one previous number to see how it affects the future number. So what can I do to 1 to make it to 3? Well, I can add 2, but I can't do the same thing to 3 to give it 7. So let's see. It seems like, well, if I multiply 1 times 2, I'll get 2, but then I add 1 and I'll get 3. If I multiply 3 times 2 and I get 6, and I add 1, I get 7. So it seems like this pattern seems to multiply the previous term by 2 and adds 1. And that's exactly what happens here. And you can verify it, which I always recommend, by just plugging in and testing several values. Don't just test one, but several n values, and see if you get the same values that are part of the sequence. Let's take a look over here. Well, this looks like 1, 4, 9, 16. These look like the perfect squares. So I can represent this as a general term of Sn equals n squared. But they want recursive, not non-recursive. So I need to use the previous value to determine the next value. So sometimes it helps to write stuff out. What do I do to the previous term to get the next term? So I add 3 to 1 to get 4. I add 5 to 4 to get 9, and vice versa. So it seems like I'm adding a value that's 2 more than the previous value that I added to get there. So I can come up with an expression that looks something like this. Take the previous term based off this and add a power. I know some of you are saying, where did the 2 to the n plus 1 come from? And this is the point I wanted to bring up. Whenever you're defining something recursively, you definitely need to find what the starting value is. In this case, it was 1. And in this case, it's 1. But since I'm using the previous term, which in this case is 1, and I add 1 plus 3, so I can add plus 1 here. So then I will get, this makes more sense. So it's kind of like we have two sequences within. We have this sequence, which is just the previous term, and then we add this sequence, and this sequence can be related as 1 plus 2 to the n, and since 2 to the n, in this case this is 2 to the 2 is 4, and we want to add the previous one, which is 2, we do minus 1. And that's how we get this formula. So whenever you define something recursively, you have to indicate the first term and also what to do for all the terms that are not the first term. And make sure it matches up. Okay, one last thing before we end, talking about convergence of sequences. And this should make more sense now that we've done limits. We can say that a sequence has a limit written just like this format if S of n is as close to L as we please whenever n is sufficiently large. That's like epsilon delta. So if a limit exists, we say the sequence converges. If the limit does not exist, then we say the sequence diverges. So if it has no limit, it diverges. From last semester, we had these processes with functions that had limits. And if we notice that a function had a limit if it looked like x to the n, where x was between 0 and 1, absolute value, and then it diverged if x was bigger than 1. And we also had a similar one in this sequence. So let's see if it works. Which ones converge and which one don't converge? Well, this one looks very much like this one, so that lets us know, hey, that x is between less than 1, so then that means it does converge. So we can say yes, converges. Over here we can say, well, e to the negative n, that looks like 1 over e to the n. And 1 over e to the n is a number that's less than 1. So therefore we know that this subsequence will converge, and we also know it converges to 0 from either this method or this method. So this converges to 0 and this converges to 0. So we can say that this sequence will definitely converge. So this is converges. Over here we can see that as n gets bigger, the denominator gets bigger, but so does the numerator even more rapidly. So this will not converge, because as n goes to infinity, this whole expression gets larger and larger with no bound. And then the last one we want to take a look at is, oops, this one, we'll move it over. Yes. And it seems like it seems like it would converge, but if we take a look at it, it's alternating between 1 and 0, 1 and 0, 1 and 0. And because it's not getting sufficiently small, as close to a limit as we want, whenever n is sufficiently large, then that means that it does not converge, okay? Because the difference between any two values is going to be either 0 or 1. All right, so how can we another way to determine if sequences are converging is if they're bounded. So here we have a sequence is bounded if all the terms always lie in between two numbers k and m, two constants. Okay, if we can find a term that does not lie, there are no two numbers for which every term lies in between, then that sequence is not bounded. So one of the things that we know is that convergence sequences are bounded because they have some type of limit, i.e. getting sufficiently close to L whenever we want. But not all bounded sequences are convergent. Just look at the example that we had last, where it would alternating from 0 to 1s. Here, this is alternating from -1 to 1s. It is bounded because it doesn't go below -1 and doesn't go above +1, but it is not convergent because it doesn't get as close as we want to a limit L. So if I want to know if a sequence is bounded, we have a theorem that says if the sequence is bounded and monotone, then it converges. So since not all bounded sequences are convergent, if we can find a bounded sequence that is monotone, then it converges. And some of you may be asking, what is monotone? Well, monotone is either monotone increasing or monotone decreasing, which means monotone increasing means every future value is greater than the previous value. And monotone decreasing is every future value is less than the previous value. Okay, and not less than or equal to or greater than equal to, just strictly less. And so if the sequence values are always increasing and it's bounded, then it will be conversion. Or if it's always decreasing and it's bounded, then it will be conversion. Okay, and a good example of that is this one right here. Well, two examples we're going to look at. This one we can see from our previous test. 1/2 is less than 1, so it will converge. But we can also use the fact that it's a sequence that is always decreasing. It's monotone decreasing, and it is bounded. It doesn't go above 1, and it doesn't go above 1, and it doesn't go below 0. So that's one example. And the last example before we end this video is this one right here. As we know, this value right here, from math, we know that with calculus, we know that the limit of this as n goes to infinity is e. So it is bounded by between 0 and E, but it's always increasing, so it's monotone. So therefore, these two sequences do converge. All right, that's it.